Part 3, full color image processing. So, there are two major categories of techniques for full color image processing. One of them we discussed already briefly. We could process each grayscale image individually, meaning each grayscale component of the image. If the image is an RGB, I should say in the intensity matrices of that compose a color image. So you apply an individual process to R, to the red channel, to the green channel, and to the blue channel, and then compose them into the color image. And the same way that we did with the grayscale image, or we can work with the color pixel directly by where the pixel is now a 3D vector that's called a voxel. So you're going to apply a transformation on the three-dimensional pixel, meaning in the pixel composed by the R component, G component, and B component, if you are dealing with in the RGB color space. They are equivalent operations if they are applied to vectors and scalars, or when the operations are independent on each component. Of course, this is just a special case of operations. Any operation can be applied to any color model, but some are more suitable to particular models than others. So, for instance, let's get the example of modifying the intensity of the image. If we have an HSV or HSI, if we want to modify the intensity of the image, I just need to get the I component or the V component, the value component, and multiply by a particular constant K. Right? Very simple operation. In the RGB component, in the RGB space, in order to obtain the same result, we have to multiply all three components by the same constant. Right? So we have to multiply the R component by K, the G component by K, and the B component by K as well. It's a few other, this is an example of adjusting the intensity of a color image when you obtain the same result, whether you're just multiplying I. And of course, if you are in a CMY space, you have to consider what kind of operation you are doing. Another detail that you have to consider on when dealing with color spaces, with color components, is the color circle or color wheel. It's created by placing the primary colors equidistant from each other in a circle, and we call the hues that are directly opposite from one another as complements. This is similar to the grayscale negatives. If you get an image, as we did in the lab, we get an image and subtract all pixels by 1, you get the negative. And a grayscale image, you get the negatives, where everything that's white becomes black, everything that's black becomes white. That's the same thing in the color space, but instead of getting the negative, we get the color component of a machine. So this point here, that's kind of cyan, closer to green, will become a kind of orange, magenta type of image. Color slicing is another simple technique that you can do. Color slicing is that you get a particular hue and you select every pixel. So for instance, let's get this image here and select only the red pixels. Then what we get is the kind of segmented portions of the strawberries, and that's one simple technique to separate objects from background. This is segmentation. We're going to have a lecture on segmentation in a few weeks. So the basic idea is to display colors of interest so that they stand out from the background. And we can use these regions that are defined by the red colors to do further processing. So they can be used as masks to do further processings only on the strawberries. So one thing that can be easily done is to cut this piece of image and superimpose on some other image, creating a composition, right? Tone and color corrections. These are similar to gamma corrections in grayscale, but you're actually dealing with the distribution of color intensities rather than on the grayscale. What you do is you modify the tonal range, also called the key type, by applying a mathematical function to one component or to all four components. So the basic idea here is to adjust the image brightness and contrast to provide maximum detail without changing the colors. In RGB or CMY and K color space, we have to map all color components except K, that's black, to the same transformation function, which could be an exponent, it could be a log, depending on what kind of result you want to get. All right, this is an exponential. This is a log-like function that's been applied to RGB, taking this picture that's a kind of a flat color and enhancing the colors of these pictures, right? Of this particular picture. The exponent here took a kind of very light, bright, boring picture into a more colorful version of it. Or the log function, taking a dark image here to a more kind of corrected, or let's say adjusted image. Of course, this leads us to another basic algorithm that we learned, basic method that we learned on the grayscale color image processing, which is the application of histogram equalization, but now on color image. The idea again is to automatically define a transformation to produce an image with an uniform histogram of intensity values. The book says that it's unwise to equalize components independently, meaning you apply a histogram equalization on red, then you apply a histogram equalization on green, then you apply a histogram equalization on blue. So a better way of doing this is to map your RGB image, RGB image, map that into an HSV space, and then we just have to equalize the intensity. We just need to apply the histogram equalization on one component, which is the V value, or if you are on HSI space, you apply it on the I, on the intensity channel. That's what it's done here. You get the original image here, and then you apply a histogram equalization on I. That's what the book did. Oops, sorry. The book did. This is the histogram before processing, and this is a histogram after processing. And what you see here is that a better distribution of the colors here. Especially take a look at this portion of the picture, whereas here is a little bit darker, and we can see the details. Where in here it's pretty much well, we can see everything that's in there. I'll get rid of this so that you can see these points better. Okay, convinced? And well, this is just a scheme about what you do on color histogram equalization. This has been taken by these lecture notes from, I think that's, if I remember, it was University of Washington. You get an RGB image, then you apply this. You can easily do on OpenCV on 2 lines of code. You transform your image to HSV by applying this well, just a basic transformation. Then you can apply a function on H, a function on S, whatever function that you want to use to enhance the picture. But you apply a histogram equalization on V, on the V channel, and then you combine these 3 matrices and turn them into an RGB, and that's the output. So that's what this guy, I think that's the lecturer that made these slides. So here you can see his face better. You can his lecture notes are wonderful, so I recommend you to consult them. They are available in the internet. Again, the same thing that we did on grayscale images, we can do in terms of smoothing and sharpening. We can do with a color image. Then the result is that we obtain on grayscale images is to remove abrupt transitions of gray values. In the RGB domain, it's the same. So we're gonna have a smooth, a kind of a blurring effect on the 3 channels by applying an appropriate smoothing mask. Of course, that depends on what you want to get out of the image. But you can either apply a box kernel or a Gaussian kernel to your image. In the HSV domain, you can apply all of these transformations only on the V component if you want to apply a spatial smoothing mask, leaving H and S components unchanged. On the RGB, you have to apply the transformation on the 3 components. But then the final result will be different. In the RGB space, the average of 2 colors is an intermediate color. So if you apply smoothing on the RGB, on the 3 components, you may be changing, depending on the case, of course, depending on the intensities that you have, you may be changing the hue of your color. Whereas if you are dealing with the HSV space, the hue and saturation components are preserved, and just the intensity or the value, depending on which space you are dealing with, is smoothed. That's a funny word. Smoothed. Now, this is the result of image smoothing. This figure A is the result of processing each RGB component of the image, and this is the result of applying the intensity component on the HSI image, then converting to RGB. And you can see that subtracting this minus this other, we are going to see what? We are going to see the differences, right? We're going to see the differences. And this is the difference. So you see that the processing is totally different. Although you don't see much changes in hue, but you see that these markings here, these are all information that have been added by the process by the averaging kernel. So no transformation is pure. You are always, when you manipulate an image, you are getting, you are transforming it in some sense. Okay. In image sharpening, you can also do on the color space, and that's the same case that you can either apply on the 3 components of the RGB channel, or you can apply on the V and in this case it's an HSI image. You apply the sharpening on the eye, the intensity component, then convert into RGB. Now this you can see that the results of sharpening on the HSI, just applying sharpening on the eye component, generated a much sharper figure. You can see better, especially on this portion here, and here is kind of a blurred, although the change out here, this is kind of very sharp, and this is not as sharp as we wanted. Okay, and that's all for color. Of course, that's all for the basics on color image processing. What you have to keep in mind is that when you're dealing with color image processing, with true color image processing, you have to consider whether to apply your processing on the RGB channel, or the RGB image, or on the HSV image, what you're going to get out of it, and if you're going to apply your functions on the 3 components or on the voxel, on the 3D pixel of the RGB component. Again, the discussion that we had at the beginning of this course, who dictates which methods to apply? That's you as a image processing engineer, computer vision practitioner, and it's pretty much trial and error, and see what you get at the end, whether this works or not. Because it depends on what kind of images you have, what is the textures involved, what are the textures involved, and the colors involved in what you want to get at the end. I'll see you for the last part of this lecture, when we are going to be talking about noise in color images.